Welcome back. So we talked about momentum, okay, by taking a physical perspective, and we discussed that momentum could help us to accelerate the convergence, meaning we can find better solutions faster. Okay. Now we're going to basically see how this momentum idea could be utilized in the context of optimization for deep learning. And indeed, we can use this idea, with, but in practice, I would say we use this idea with some modifications. Okay. So first of all, we typically use m to denote the momentum as opposed to p. Okay. But in physics, m is reserved for mass, so we don't use that for momentum. That's not very important. Another modification is that we typically are working in the stochastic setting, meaning that we don't have access to the true gradient of the loss function in each iteration. We only have access to a stochastic estimation of the loss, a gradient of the loss. Okay, for instance, we are working with a mini batch of samples as opposed to the entire data set when we calculate the gradient in each iteration. Okay, and the final sort of modification is that we're going to basically use this variant. Okay, so the first equation is identical to what we had before. Again, we use a first order update. We move along a specific update vector, in this case mt, with the learning rate eta to go from wt to the next solution wt plus 1. Okay, but the momentum is updated in this form. So there are two terms again, beta times the previous momentum. This is exactly like before, but previously we had the gradient here. Here we have the stochastic gradient times 1 minus beta. So this is what we didn't have in the heavy-wall method. Okay? So that's one of the differences. And as we'll see, this is something that's going to lead to what I refer to as the bias variance trade-off perspective into momentum. Okay. And in terms of initialization, we set the m0 to be 0. Okay, so this is not something that's gonna arise in the optimization algorithms. Okay, so this method, therefore, let's call it a different name. Instead of heavy wall method, we're going to call it SGD with momentum. Okay, where the momentum is not just beta times the previous momentum plus gradient, it's the convex combination between the previous momentum and the current stochastic gradient. That's the major difference. Okay, and you can also basically interpret the momentum as performing exponential moving average of all the stochastic gradients we have observed so far. And to see this, all you need to do is to basically expand this recursive equation through time. And if you expand it, you're going to arrive to this equation. Okay, so this is nothing but, again, taking the exponential average of all the gradients we observed before with weights beta. Okay, so in some sense, again, this puts more weights towards most recent observations. In this case, the stochastic gradients. Okay, compared to just a linear averaging of the gradients. Okay. Right, so therefore, as I mentioned, we're gonna now talk about this momentum idea from the perspective of bias variance trade-off. Basically, we're gonna view this as now a new estimator of the true gradient, as opposed to just the simple G sub t that we get from our oracle, which is basically an unbiased estimator of the true gradient with some bounded variance. Okay, so in particular, let's recall our SFO assumption. We assume in each iteration we can access an oracle and get an unbiased estimator of the true gradient, which we call GT, with bounded variance. Okay, and this is something that we expect to happen in practice. For instance, when running mini batch SGD, right? So we select a batch of samples from the training data, calculate their gradients. If our selection of the mini batch is, let's say, uniformly at random or something like that, then that could serve as an unbiased estimator of the gradient of the entire data set. Okay. So this is something we talk about extensively when we discuss SGD and its analysis. For SGD with momentum, we are not using G sub t as our update vector. We are using this vector, which is more complicated. Okay. Now let's talk about this from, again, perspective of estimation. So this is an estimator of the true gradient. It may have some bias, it may have some variance, so let's see what those are. For G sub t, that study was very, very simple. It was unbiased, meaning bias is 0, and we assume that the variance is bounded by sigma square. In this case, however, it's going to be more involved. Okay, so in particular, this actually leads to a biased estimator. Okay, so this is our estimator at time t. It's updated using this equation. I'm just taking conditional expectations by fixing the previous selection of mini batches. Using the linearity of expectations, we can basically break this expectation into two parts and bring out the constants. This part is easy to deal with because we assume we have access to an unbiased oracle. So this conditional expectation is exactly the true gradient. On the other hand, for this term, that's not necessarily true. Okay, so this term is not going to be the true gradient at Wt. Therefore, this conditional expectation is not the true gradient at Wt, and we have some bias. Okay. So at first glance, then this might seem a bad idea, right? Because in simple SGD, we work with something that doesn't have any bias, and we basically show that it has convergence. Okay. In this case, however, we are actually, by performing this, by integrating momentum into our optimization algorithm, we are picking up some bias. Okay. So that seems a bad idea. However, when we talk about the estimation performance, okay, so recall, let's say the error basically is has two parts, right? So one part is bias, the other part is variance. So bias is going up here, but we haven't studied the variance. Maybe the variance is going down by a lot, such that the total estimation error is actually going down. Okay, so therefore this might be actually end up being a good idea. And in fact, this is something that is happening. Okay, so by gaining some bias, we are reducing the variance, and as a result, we actually observe a reduction in total estimation error. But the analysis is a little bit involved, and that's basically what we want to do in this lecture and the next lecture. First, we want to gain some intuition, and then we're going to see how this is going to play out in the context of convergence analysis of this algorithm for training problems. Okay. So let's, as I said, gain some intuition. So I'm going to make some assumptions that don't make sense necessarily, but we're going to see where that leads us. Okay. So again, we're going to work with this expanded version. So M0 is 0. This was the way that we were updating the momentum. Expanded through time. This is what we're gonna get. Okay. Now, as you can see here, the momentum is a function of all the stochastic gradients observed so far, right? And obviously, these depend on each other, right? Because to get the next gradient, I have to calculate the current solution, right? And the current solution depends on the current gradient. So the next gradient depends on the current gradient, and so on and so forth. So these actually depend on each other. These vectors depend on each other. But we're going to assume that they are, let's say for the timing, they are independent. They don't depend on each other. And also each one is an unbiased estimator of Wt, gradient at Wt. This is also not true, okay? Because again, remember, G, for instance, t minus 1 is actually the stochastic gradient evaluated at t minus 1, okay, and zt minus 1. So this is not the same as the stochastic gradient at Wt and zt. This guy is an unbiased estimator of the true gradient Wt, but this guy is not. Okay, but we're going to assume that actually is also a good unbiased estimator of the true gradient. And also we're going to assume that its variance is sigma squared. Okay. Now let's talk about some takeaways. Okay. So first, let's calculate the bias, or rather the expected value of the momentum under this assumptions that are not necessarily true. Okay. The expectation can be calculated quite easily using the linearity of the expectation and the assumption we made. Okay. So we assume that each one is an unbiased estimator of the true gradient. So after taking the expectation, this comes out of the sum. This is a constant, so we're going to be left with this geometric sum. So we know that we know how we can sort of calculate geometric sums. There is a formula, so using that formula, we're going to basically arrive at this equation. As we can see here, there are 1 minus beta in the numerator and denominator. So let's get rid of both of them. So we're going to arrive here. Okay. So therefore, what we did under these assumptions, we calculated the expected value of the momentum. And this is basically the true gradient times 1 minus beta to the power of t. Okay. So our first takeaway is sort of what we expected. This is actually, even under these simplifying assumptions, still a biased estimator of the true gradient. Okay. However, the bias is going to vanish as we train our model and t goes to infinity. Okay. So let me be a little bit more explicit. The bias here in this case, so the bias is basically the gradient times beta to the power of t, or rather minus the gradient times beta to the power of t. Okay. So these two parameters are not necessarily zero, therefore the bias is not zero. But if I'm at a solution, the gradient is zero, therefore the bias is zero. So therefore, as we are converging, the bias is reducing. On the other hand, beta is a parameter which is, again, remember, is between 0 and 1. So beta to the power of t, therefore, is a decreasing function of t. So again, as I keep running the algorithm, the bias therefore goes to 0 at an exponential rate. Okay. So that's the first takeaway. But this observation actually provides a way to get rid of the bias. So as we can see here, if I didn't have this factor 1 minus beta to the power of t, under these simplifying assumptions at least, my momentum would be an unbiased estimator of the true gradient. So therefore, let's use this idea. Okay, so we can debias the momentum by dividing it with 1 minus beta to the power of t. So therefore, this is going to be what we typically use in practice when we mean SGD with momentum. So we have our usual way of updating the momentum, but instead of using that to update our parameter, we're going to first divide it by 1 minus beta to the power of t to debias it, and then use the result to update our parameter. Okay. So that's the first takeaway. We have some bias. We can do a debiasing technique to reduce it. All right. So now let's talk about the variance. Okay. Again, using our simplified assumptions, and let's consider the variance of this debiased momentum. Okay. Under our simple setting, which again meant each gradient we have observed so far is an unbiased estimator of the true gradient at time t with bounded variance. And also, we assume that the stochastic gradients are independent. Okay. Under these assumptions, the variance is basically the expected norm difference of basically the momentum, here the debiased version, minus the true gradient. Okay. So we can plug in the definition of m hat, so to arrive at this equation. Okay. Now, it turns out that basically this sum is going to be exactly 1 minus beta t divided by 1 minus beta, as we saw in the previous slide. So what I can do is basically I can put this guy, the true gradient, inside the sum. Okay. So inside the sum such that it gets the weights beta k. Okay. So in particular, basically, what I'm doing here is that this is exactly equal to 1 minus beta t sum k from 0 to t minus 1 beta k, the gradient at wt. Okay. Because this sum is exactly the reciprocal of the coefficient behind it. All right. So we do this, we merge it with G with the stochastic gradients. And the reason for that is that because we're going to use the fact that these are unbiased estimators with bounded variance sigma square and they are independent. Okay. So therefore we can use the fact that variance of sum of independent random variables is sum of the individual variances. So we can use that idea here to arrive at this equation. Okay. Now this is basically the variance of each of the stochastic gradients. I'm assuming that that's bounded by sigma squared. So I'm going to therefore upper bound it to arrive at this equation. Okay. Now this is this might look complicated, but in fact it's not. It's just some constant times another geometric sum. So we can use again the formula for geometric sum to simplify it to this case, okay, to this expression. Now let's call this constant. It's not very important what this constant is, but let's call it b sub t. And I'm going to talk about its properties in the next slide. So long story short, under these simplifying assumptions, we show that the variance of our momentum is sigma squared times 1 minus beta divided by 1 plus beta times the constant b of t, which depends on time. Okay. So let's see what are the nice properties of these BET. So it's not too difficult to actually, for instance, plot this as a function of time and notice that it's a decreasing function of time for any t larger or equal to 1, and it approaches 1 as t goes to infinity. Okay. So therefore, what's one conclusion we can make here? Given that the variance is proportional to b of t, and b of t is a decreasing function of t, the variance reduces over time. Okay. So therefore, not only the bias, but also the variance of our momentum parameter, momentum gradient estimator is going to reduce over time. Okay. So that's one idea. Another idea is to basically again use this assumption that b of t is equal to 1. Okay, and this is not a bad assumption because as t goes to infinity, b of t becomes 1. So basically, we want to see what will happen when we have trained our model for a sufficient number of epochs. Okay, after a certain number of sufficient number of epochs, then the variance, which was sort of under our simplifying assumption calculated to be given by this expression, is approximated as 1 minus beta divided by 1 plus beta times sigma squared. Okay. Now let's assume that we are using a large momentum parameter. And by large, I mean beta is very, very close to 1. For instance, beta is 0.9. So if I replace that here, I have this constant times sigma squared. After simplification, this is going to be sigma squared divided by 20. Okay. So effectively then, when my momentum parameter is 0.9, under this simplifying assumption, the debiased momentum vector is acting like a mini batch SGD with batch size 20. So we are basically still working with, let's say, batch size of 1. We are working with 1 sample at any time. Okay, but given that we are also leveraging all the previous stochastic gradients, we are effectively increasing the batch size. In particular, we are again leveraging the previous observations to artificially increase the batch size, therefore reduce the variance. Okay. So this is, I would say, a nice perspective into momentum, where by leveraging this update, we are reducing the bias, we are basically gaining some bias, which is vanishing as the algorithm converges. But on the other hand, and more importantly, we are drastically reducing the variance, such that collectively, the estimation error associated with the momentum is in fact smaller than the estimation error for just a simple SGD algorithm. Okay? But let me also mention this important remark, that this intuitive analysis is not precise by any means, okay? Because we are making lots of simplifying assumptions, which none of them is true, okay? And even this debiasing might suffer from some bias, okay? So that warrants a more formal study that we're going to basically do and develop in our future lectures. So before that, in the next video, we're going to talk about how we can put in these components we've talked about in the class so far, momentum, adaptivity, and per coordinate step size, as well as this debiasing idea I mentioned, into one single training algorithm, which is called ADAM. I'll see you next time.